pull up notes first, so maybe I can wait for a minute.
Okay, let me load my notes there. And I would like to go to signal flow graphs for today. Yes, go ahead and tell me.
Okay, well, this has to do with the microstrip implementation of the filters
Yes.
in the homework,
Uh-huh. Yes.
and I guess isn't really on this set of notes, but that's okay. So my question really was, in the homework, at some point we have to implement a series capacitor and inductor,
Yes.
uh, and to do that in the notes it says to do I think it's a series stub, and I was just wondering, like, in microstrip, is that possible? Is that like valid to do?
So,
Uh,
so obviously when you solve, did I say in the homework that you have to do it with a microstrip stub?
I think you said we should use microstrip. I don't know if you said
Microstrip
start
only, not
stub.
stub. Exactly. Yeah. So here is one thing that you will learn from this experience, that you can have an absolutely wonderful design on paper, and then when you try to make it, you're going to have a number of constraints that will make you think differently about your design. I always want to tell you that as engineers, we always find ways to implement the design. The question is, which of those is going to go closer to your intended design? All right, because every time you go from theory, which is practically your RLC circuit is theory, all right, until the point where you have calculated all of your RLCs um, according to the insertion loss method. All of this is theory. And if you put theory, that theory not in LC and RLC into MATLAB is going to give you the exact outcome. Where it starts becoming a reality is when you have to materialize it, and I specified microstrip. And so there are two issues that you are facing, and I will touch on those and as part of this lecture because I think it's important, and then you can ask me more specifically during the office hours. So number one, in your designs, you have inductors and you have capacitors. And your inductors can be either series or shunt, and your capacitors the same. All right, you can have any combination of series or shunt between those two. And series combinations in series connection, shunt combinations in series connection, whatever your design has after you perform all of your transformations. Okay, microstrip now. That is all good so far. All right, when you have LC, anything is possible. But when you go to microstrip, and microstrip, if you remember, looks like this. All right, and just this is your conductor here, and conductor, and the rest is dielectric in between them. All right, the microstrip has, the dielectric has a thickness, and how much did I give you, 100 microns or more, or 200 for this homework?
500 microns, I think.
Okay, 500. Okay, so H is 500 microns. And W, I did not give you W because I gave you epsilon, and that was what, 3 point something?
You gave it as 4.
4, okay. And W then is gonna come as an outcome of your number of things. what is going to specify W? First of all, characteristic impedance, Z0, specifies W, all right, for sections of lines. And L value is going to specify your width of the microstrip for that section that has to provide you an inductance. Your C also is going to specify your W for a section that has to provide a capacitance. Now, in microstrip, you need also to remember, if I draw my microstrip like this is a top view, all right? So this is my microstrip. And then,
Katehi,
yes?
what is the unit of H? Mu? 500
Micron.
Oh,
Yes.
Okay.
Micron. That's how we indicate microns. All right. So, now, when you look at the top view, when we make an inductance, it looks like this. We narrow the width, all right? And that gives us in a series inductance. When we do increase the width, what does it give us? Who is going to tell me?
Shunt capacitance.
Exactly, shunt capacitance. And then it's like this, okay? Let's assume that, so you understand that. All right, what happens if I have a shunt inductance now? Or a series capacitance? What do I do with those as it happens? I mean, that you have exactly in this one. What did we say that we are doing? For an LC shunt, all right, let's assume for an L alone, it's very difficult to do a shunt inductance alone, all right? Now, you can do it. Obviously, you can use a stub. You can definitely use a stub, which is shorted at the end, and then you calculate L. So it gives you a particular inductance here. Excuse me, sorry, I was thinking about the characteristic impedance of the stub. So JX, okay? So you can do an inductance there. I mean, it's more difficult for microstrip because you have to use a via hole, as we call it. You have to connect to ground. It's okay, but you can do it. There are via holes in wafer. People design them on all kinds of toroids and everything. Okay. How do we design a series capacitance in microstrip? Do you remember what we did in the MIMs? If this is your microstrip line, that's your ground, but now it's a longitudinal view. That's your ground. Your microstrip line comes from here. And then you need to put a series capacitance. How are you going to do it?
You have like two traces and there's a gap in between them and they overlap.
That is a little too small to do. Yes, they have to overlap. Absolutely. They have to overlap because if you just bring one close to the other, this gap and like this, if you only bring them like that, yes, it is a capacitive gap. It's a series capacitance here, but it's small, so the capacitance is going to have a small value. If your series capacitance has a very high value, in that case, what we do is that we bring one line here, but then we put a dielectric here, and then we connect the other line here. So your metal goes like that. You remember the MIM capacitors? And this region here, all right, that's your metal. And this region here gives you the capacitance. And it can be very high capacitance, all right? So you solve that. So high series capacitance, no problem. High shunt inductance, no problem. All right, you can do that. I mean, you know, it's not your. It has some kind of activity, not just a simple microstrip line. Here you have to put a via. Down here you will have to create that, but they can be done. The pros are available. What happens if you have a shunt LC? Very similar to this one. Okay, we just have to change L accordingly as you see in the book to create that kind of performance. Now, all of these so far involve approximations. This is an approximation to an inductance, obviously. We have simplified, we have avoided a number of edge effects and so forth, and other approximations of a capacitance, and other approximations of a capacitance, one of the inductance. All of these approximations will not necessarily in reality affect your pass band, but if you were able to go to one software like HFSS, that can very accurately characterize all of your microstrip geometries, you will see variations, especially as you approach the cutoff frequencies, and then you go outside of your band. But in any case, in the pass band, I think you're going to have a good approximation of your design. Where are the additional problems? Now, we have additional problems in the following, which you just faced in your design. Let me just go to this. In your designs, you had a very weak inductance and a very strong capacitance. Am I right?
Yes.
I don't
Okay.
remember,
Yes.
Yeah.
Yeah.
Yeah, very large C, small L. So this high, this low. Okay, what does that mean? That means, let's look at the L first. It means that if you try to do it with a stub, and let's assume you were trying to do the L first, then the stub by itself to have a very small inductance is going to make this to be either extremely small, both this very small and this very small, all right? I mean, low, and they like the characteristic impedance. I'm sorry, this is not a good visual for the characteristic impedance. So let me do this again carefully. Yes, a very small value for the length, and for the characteristic impedance also very low. So low that your width is going to become humongous. So forget it, Z naught less than 20 ohms or 15 ohms, don't do. That's number one problem. Then your capacitance, which is capacitance to the ground, and usually capacitance to the ground is like here, all right? For a capacitance to the ground, as we've seen before, you rely on this electric field, which is between the microstrip and the ground, to be able to materialize that shunt capacitance. Do you agree with me?
Yes.
All right. Now, if this capacitance C is very high, what is it forcing you to do? Either to reduce this to a very, very thin layer, which you cannot do because I gave it to you 500 microns. You cannot go below that. So for that, either you reduce H, or what do? You increase W. And if your C is very, very high, your W becomes ridiculously high. So, or in other words, equivalently, your Z naught goes extremely low. So these two approaches are not working. Okay, so I have two ideas for you. And that's what design comes about. The people who have from experience, obviously, all right, but the people who have the capability to find solutions, they provide the best designs. Or if these, you exhaust all of your, in a real world, now not in the homework, but if in the real world, somebody asks you to do a design and then you follow it a particular way and then you don't go anywhere, then you have to go back to question your method for solving the problem. And then we have not covered a lot of things. So like coupled lines, we have not done, and things like that, which can alleviate these problems. But let's see what I would do if somebody would come, my boss would come and say, we have only microstrip, we have this, we don't want to use coupled anything for all kinds of reasons. You realize this for me. So now I have to think, okay, I have a very small L. If I have to realize an inductor using a shorted stub, all right, and this inductor is very low. So how much is the inductor value? Here, J sub X will be J Z naught tangent beta L. And my X will be omega L. If my omega L is a very small number, that implies that my Z naught becomes very small and beta L becomes small. What if I want to make Z naught 50 ohms? So then if I make Z naught 50 ohms, I need to make tangent beta L even smaller. Do you agree? So the small L becomes even smaller. Now, what do I do next if that's the case? Instead of, if you remember, the tangent beta L goes like this. Do you agree? Like this. And repeats itself every how long? How much is this distance where it goes through 0 and up again? Do you remember? Beta L here is what?
Is it pi?
Pi. So your L becomes lambda over 2. Now, let me tell you, we have a storm here. If we lose power, you're gonna lose totally me because I will not have access to Wi-Fi. So I have just to prepare you for that. In any case, so practically it goes there, which means instead of me looking down here for beta L, I can look up here. So if I look up here to get this very low value, the L value is going to be close to lambda over 2 plus a delta L. Okay. So I can materialize L, but it's going to be half a wavelength practically. And it depends on how high my frequency is. Half a wavelength in the material might be too long for my applications, but you know, I was gonna look into this. So that is one way to check to see whether you can do that. The other thing is to look into the capacitance. Now, your capacitance is still a big problem because with your capacitance, you have to bring the ground very close. So here is what I would do. Let's think that both my inductance and my capacitance are very small. So instead of using sections of transmission line, which is also going to be another way of doing the inductance, what if I do like lumped elements, what we call? So if this is my microstrip, what if I bring my ground? First of all, I would like to do all of my geometries symmetric. So instead of having one L and one C here, all right, in the line, what if I have two of those? So my L and one C here, and another L and then C here. All right, so what that helps me, I increase my inductance, I double it, and I make my capacitance half. Okay, it's all positive so far. So at least I have been able, that may not necessarily help me because a very small number twice is still a small number. And a very high number divided by 2 is still a high number, but I made it symmetric. And then, so what I would like to do is I need to bring the ground close to the line. Because if you remember, I have a capacitance that is like this. I cannot create a capacitance like that because this is my signal line and this is my ground. So I need to bring the ground to the line. So if my line is this is a top view of my microstrip. So I will bring the ground to the line, which means if I were to erase that and do a side view, in fact, I will do a 3D for you. If my line goes like that, and if my ground is here, and that's the dielectric, all right, then I create a via hole here, which I can do, and bring my ground up here. All right, on both sides. And then I can put a pad around it. Usually we do that. And then what I do now, I put a dielectric over it. And then what do? Then I put a metal over it, and then I connect the metal. So practically what I have to do, or maybe you can only put the dielectric in 2 sides. So if I cut it here, and I show you that view, it's gonna be your microstrip. That's gonna be your via. All right, with a pad here, all small, so it does not matter really. I'm trying to show you how you're gonna fabricate it, and then you put a dielectric, and then a metal. So now I have my capacitor here. That's how people will do it, okay? So it's a shunt capacitor. Now, why the inductance? How would I do the inductance here? For the inductance, I need to connect the pad. The pad is the metal. I need to connect the pad to the conductor. So I will put 2 metals here to connect it. And that's going to give my inductance, because it's a very small, any section of narrow line is going to give me an inductance, and it's going to connect to my metal of the microstrip. Now, why I'm saying that, we are not going to do this. MATLAB cannot do this for you. My only advice to you is for a very small shunt inductor and very large shunt capacitor. You do not you assume they are lumped elements. When you have a lumped element, in MATLAB, you introduce it as a lumped element, as an L and C, not as a section of line. Okay? And then if you have to go to the lab and materialize it, that's how I would do it. So that's how I would do my design in this particular case. So again, what did you learn from all of this that I said? That if your L is very, very low, and it's shunt, and if your C is very, very high and it's shunt, then use them as lumped elements. Just say, I'm gonna create them lumped elements out of microstrip. There are a lot of different ways of doing lumped elements in microstrip, all right? MIM capacitors and inductors, just short sections of narrow lines. However, in the other ones that you can realize using transmission lines, do them, because as you can see, doing lumped elements, it requires more fabrication steps, and at the end is more difficult and more expensive. So nobody wants to go to unreasonably complex fabrication steps for something you can do like a transmission line, using a transmission line, all right? Did this cover your questions?
I would say so. I guess I just wanted to make sure that I did the homework correctly, or
Yes.
I didn't make any big mistakes.
No.
So yeah, I think it answers my question. I just want to make sure that like, it's like on the notes, like a couple of classes ago, you suggested a way to implement a series capacitor and inductor
Yes,
using
for reasonable
series
values,
stub.
all right? Exactly. For stubs, but when you, and that's what you go for first, all right? You go for a stub because that's the easiest one to do. But when you find that the values you get in your capacitance are unreasonable, then you look at something different. And that's why I try to explain what kind of thought process would take me down to saying, oh, well, this else is so small and it's shunt, this C is so high and it's shunt, I'll make them under as lumped elements. And
Okay.
then you move on, okay? And that, you keep this in mind for all of your designs. Keep this in mind for all of your designs, whether you have to do them with microstrip as we do, or in real life using another line. If you come out from your designs with unreasonable values of length or characteristic impedance, then you know that using transmission lines to realize them is not possible. And then you go and you look at other options. Okay.
That sounds great. Yeah, I found all of this other explanation to be really helpful, actually, and insightful. I just had other questions about the homework too. This is good. I really appreciate it.
Sure. Okay, now let's go. If you have more questions about that during office hours, what I would like to do today, and I will tell you what we will have to do to finish with amplifiers. I took a big, if you like, rerouting, and then I introduced the signal flow graphs, and you have them here. And then there are rules and all of this. I have them for your information. But the most important piece of a signal flow graph is Mason's rule. That says the following. If I have a fairly complex, for example, network consideration. In fact, those signal flow graphs, I thought I did not want to miss the opportunity to introduce them because they are used in control circuits. You will find them in electronics. I mean, people in industry are using them extensively. So I did not want you to be oblivious to it, that they exist. The most important rule that I use in signal flow graphs are Mason's rule, because it's more straightforward. The rules that we, in fact, talked about, which is like a series rule. What do you do if you have three nodes and the middle node does not have any other line connected to it, that you have this combination? What do you do with a parallel rule? All of these are interesting. However, and then transmission line rule, all of this interesting. The issue here is that if you have a fairly complex circuit, those rules may not necessarily help you. And so what I would do, what I found useful in my work, is to go directly to Mason's rule that says that if you have any combination of now you have replaced your circuit with nodes, all right, and with lines. So, and how do you do that? Let me go back and remind you here. This is a two-port network with an input port connected to a source, output port connected to a load, and then we have replaced this by that. You need to remember that A's, the A1s are what they go into the load, into the network, A1, A2, And the nodes that leave A1 and A2, the nodes that connect to this, with the exception of a node that comes from the source, which is this one, with the exception of the source node, and the exception of the load node, the A's of a two-port only send out, like S22 has an outward direction, S12 an outward direction from A2, from A1, S21 outward, S1 outward. However, that changes when you're connected to a source and when you're connected to a load. So what I want you to do for a two-port, because this is where we have right now, I want you to remember that. Now, you may have, instead of just a two-port, in between your source and the two-port, which may be an amplifier, you may have a matching network. It's not going to change the rule about the source and the rule about the load. If you have a matching network, it's like you're going to put two ports together, all right? So in any case, but remember that, this one I want you to remember how we set it up. Then from there, I will not go to the rules, but from there, I would go to Mason's formula. Mason's formula says that if I had this now, signal flow graph, I can find all of the ratios, like I can find the value between any of the B's and A nodes in relation to the source node. All right, so I can find B sub n over B sub x. As long as the node in the denominator does not have any other nodes connected to it. All right, so you need to remember that. Does not have anything going into it. You can put in the denominator only nodes that do not have anything going into them. All right, so I use the source, obviously. Then it shows some summations. The summation on the front has a P sub I, which is a path. We define the path. A path is any connection, say between 1 and 4 here, is any connection that has the same direction, all right? So all the arrows flow along the same direction. Now, in this path, the value is A, B, C, all right? It's a path. You may have nodes 3 and 2 connected to other nodes. You don't care about that. You just look at one flow, a path that has the same flow between your point 1 and 4. So ABC. You may have multiple paths in your circuit, as you will see later, but this is one path. You identify all of them. Then in your Mason's formula, which is here, you have these L's. These are loops. And then you will have a sum of all the first order and all of this. Let's go and look at the loops. What are those loops? The loops are, in fact, anything that closes, all right? So if 1 and 4 were to close, so we have something like this is node 1. We have node 2. We have node 3. And then we have node 4. And now there are lines that go like this. That's a loop. And the value of the loop is the product of, like, if this is A, B, C, and D, the value of the loop is A, B, C, D, okay? And then second order loop is when you take all of the loops like this, which do not touch, and you create the product and so forth. You create different ordered loops, but you have to go from one order to another. You only go if you have a lower ordered loops that do not touch. Otherwise, if your lower order loops touch, then you cannot go to higher order. So that's the other. And then when you sum those up, and you will see an example, you put them in the formula, and it says you create products between every path and what it is in parentheses, which is 1 minus all the first order loops plus all the second order loops, but this I shows that none of them should touch the path. And the denominator is the same for every ratio, is 1 minus all of the first order loops plus all the second order. And then, so you solve your problem. So I wanted to show you how I would do it for a two-port. In a two, because then we can find the gains and all kinds of things, all right? Because practically your B2 over B sub S, which is your source, B2 is here, is the outcome, the voltage that comes out, over BS will show you what is coming out of the two-port, and A2 over BS will show you how comes in to the port when it's connected to the source. And the sum of A2 and B2 is the total voltage at the port. So I can find V2 over Vs just by finding the two ratios, B2 over Vs, A2 over Vs, and then summing them up. So that's what I'm gonna do. So look at this one. Let me now, okay, here is what I told you. That if I find A2 over Bs, which Bs is practically Vs, is the value of the source 1. If A2 over Bs and I find B2 over Bs, the sum of the two will give me V2 over Vs, and the same thing with A1 and B1, they sum up to give V1. And if I sum up the two ratios, A1 over Bs and B1 over Bs will give me V1 over Vs. So now, how do I do that? First of all, I go through the loops, because the loops are important. The loops will exist regardless of what ratio I have to calculate. I look at first order loops. What is a first order loop? Gamma S, S11. That's one loop. You see it? One loop. Another loop. This one. That's another loop. Then I go and find yet another loop, this one. You see that? So I write those loops down, 1, 2, and 3. And how do I write them? Just the value. In the big one, the value is the value of all of the numbers that you have. So S21 times gamma L times S12 times gamma S. And the smaller one, like this is a small one, okay, let me see. Here. Why does it not do it? Huh. Okay. Ah, there we go. So you see this is S22 gamma L. And in this one is gamma S S11. So then what I do is I go and see whether I have second order loops. The only way I can have a second order loop is if there are any first order that do not touch. How many first order loops I have that do not touch? Here, 1, 2. So if I take these two loops and multiply them, then you get this one, which is a second order loop. And that's about it. I have nothing else. So now I'm looking at the paths, because the path depends on what ratio you're looking at. For ratio between BS and B1, let's look at the ratio between BS and B1. So I'm looking, BS is here. You see that? That's BS. B1 is down here. Let's see what paths take me to B1. It's this and this. Well, I don't need that. So the path that I get to B1 is this one. I cannot do this as a path because I go through a node twice. A path, it can only be a straight pass, only once. You pass a node only once. So I cannot use this, but only this single path that you see. And the value of this path is S11. All right, so you see that S11 here. That's one path. Let me see whether there is another path from BS to B1. There is another one, obviously, and it's this one. Look at that. It goes like this, goes like that, and stops here. That's another path. And the value of this path is S21, gamma L, S12. And I have it here. Okay? So what do I do now? Let me stay with this ratio for the time being. If I wanted to find this ratio, which is between BS and B1, then practically by using the formula, I'm getting exactly that. And yeah, you may say it's not eloquent because I don't reduce it, but it's easier to find because trying to reduce a signal flow graph, if you are not very experienced, it may get you into serious trouble if you make a wrong reduction. With Mason's rule, if you just write your loops, they will all be the same for any configuration, for a configuration. They will always be the same, regardless of what ratios you're gonna try to calculate. The paths will differ, but then you apply Mason's rule and you get exactly what you need. So if you do that, and I will ask you as an exercise in your homework to use Mason rules to now find, let me go to the values for the various gains. So I will, in fact, ask you as part of the homework to use Mason's rule and signal flow graphs to find all of these values, which are it's going to be very easy. You're going to see how easy you're going to find them without having to go through scattering matrices and calculations and the whole thing. All right, so now, of course, as you go down to power, they become more complex, but the moment you have all of this in place, it becomes easier then to get the powers and so forth. Now, in this two-port, also I wanted to tell you, for a two-port like this, which is what we're going to see in low noise amplifier design or any amplifier design, these formulas is what you need to have. So you need to have these formulas available because you will need these formulas to use them for everything else we are going to do afterwards. And the last few minutes, I wanted to take you to the following, to the following definitions. Now, amplifier stability. You remember when we solved amplifiers in the project and the homework, we talked about unconditionally stable. And unconditionally stable means that if your amplifier is like this, you see that here? If your amplifier is at the center, you get unconditional stability when your gamma in and gamma out are less magnitude, less than 1. And why is that? And then it's true for every value of of your source and the load. If this is true, that means your amplifier is stable. And from circuit theory, when you did the op-amps, what if you were to remember about stability there and about the feedback mechanisms that we used, do you remember how you were stabilizing your active devices so they would not oscillate from like circuit, the fundamentals of circuits when you were doing that? Do you remember the time when you were talking about feedback? Why was it positive feedback more important than negative? Or less important, like negative feedback more important than positive?
Because positive feedback is unbounded.
Yes, what does positive feedback do? It keeps increasing the incoming excitation, all right? So instead of when the amplifier, think like sometime between in time, your amplifier, you design it with, it has reflections at the ports. If your feedback, so like your incoming signal comes into the amplifier, but your reflections make then intensify the input signal, and they keep intensifying it over time, then your amplifier goes out of control. It burns out practically, or it's going to start oscillating. Even you cannot, practically, you know where you see that? You see that in microphones. Do you remember when they were trying to explain to you what happens with, or you hear it here? In fact, why you go to microphones here on Zoom? Do you see what happens when I have both my laptop and the iPad? I have the not only muted myself, but I have to turn off the input to the microphone. Why is that? Because I have a positive feedback back to my microphone, and then it keeps resonating. You hear that thing, and not only it keeps coming around, but it intensifies. You hear that a lot of times when people use a microphone to speak, and all of a sudden it goes off and the volume keeps increasing. That's when you get positive feedback into your system. So your amplifier keeps receiving higher and higher input, and of course the output is going to keep increasing, and that's when you have that. So that's what is going to happen here if your gamma in and gamma out, or your gamma S and gamma L that you try to match, either simple or in conjugate matching, one of them becomes above 1. If they become above 1, you have then a positive feedback into your amplifier, and then it starts oscillating. So the fundamental condition for stability is that the magnitudes of gamma in and gamma out, or gamma L and gamma S, are less than 1. Now, on the basis of that, you can have unconditional stability when this happens no matter what load and source values, so source impedance and load impedance you put, as long as they're passive, all right? So they're not negative. No matter what values there, with a real positive real part you put there, that these expressions remain satisfied. If now there are some values of gamma L, ZL, excuse me, and ZS, which make the gamma in and gamma out magnitudes, or gamma L and gamma S magnitudes, higher than 1, any of them, not all of them together, any one of them, if any one of them becomes more than 1 for any values of ZS and ZL, so then you say that you have a conditional stability, all right? And you have to find, in the case of conditional stability, the values of ZS and ZL you could match to, so you stabilize your amplifier. And that's what we are gonna do. starting next time. And I think it's gonna probably, since we're gonna talk about stability circles, then we're gonna talk about how to design for maximum gain and how to design for minimum noise. And I believe next week, we're gonna be able to do that Monday and Wednesday. So by then, you should be able to have at least the initial material for the amplifier design in place, and then we'll do different examples. Okay, that's what I have. Any questions?
I have a quick question about clarification for the homework.
Yes.
For number 2, when we're simulating our filter design, are we just doing that at the circuit schematic level, or are you expecting us to find a way to simulate the microstrip?
No. Only in the circuit schematic.
Okay, just want to
No.
make sure.
Yeah,
Okay.
because you don't know, to be able to simulate microstrip, you have really, and even if you use MATLAB, it's going to use ideal practically. That's what MATLAB
Yeah,
does.
yeah.
If you really want to do a simulation, you have to go to HFSS. And no, I don't have an expectation for that at all.
Okay, thank you.
Just to be clear on that, so we're designing the circuit of microstrip, but the simulation is then for a lumped element circuit.
Yes, the simulation is going to be for LNC.
Okay, thank you.
What you could do, I mean, it's up to you. I don't need more than that. What you could do is for those circuits, you could replace with sections of lines. You can incorporate in the MATLAB and use the small one, that whatever you're not going to make from sections of lines, do them like lumped elements. See, I mean, that's a hybrid kind of thing, but I don't expect that, only if you wish to do this out of curiosity.
Also, what kind of verification results are you expecting from the simulations? Like, do you want us to show every single spec in terms of like the 0.5?
No, just plot. Only I would plot the for the filter. Let me see. What do we? Just 1 second. Let me see what I covered in class. What I would do for the filter, I would plot only the power at the load versus frequency over the power delivered by the source. And that if you can do this, in fact, you will see whether you have the performance of the filter. You will see whether, it's like, this is also called the transfer function in the frequency domain. You're going to see how the filter performs. I don't need anything in between.
So the power at the load is a function of frequency divided by the power at the source.
Yeah, you take the ratio, so it's a plain number, or you can just look at the power at the but I would normalize it practically, and then you find the power at the load, and then you plot it over frequency.
Would something like a Bode plot or like a frequency response plot be sufficient?
If you don't want to use MATLAB, yeah, sure, you can do Bode plot. Absolutely.
Okay.
Yeah.
Oh, I have a question about the quiz actually.
Yes. Yes.
In the quiz, you mentioned the like stability circles. I don't know if is this quiz due today? Or?
Yes. That's right. I was not able to cover it, so no, not today. It would I had it designed to be completed by Monday, but now since I did not cover the stability circles, I spend a lot of time on the homework. I will ask that you submit it by Wednesday, because I will cover stability. I will send a note to everybody.
Okay, sounds good.
Thank you for telling me. I forgot about that. Yeah. I did it some time ago. I forgot about it. So yeah, thank you.
I also have a question about the practice problems you posted on October 16th.
Yes.
There is a, I don't know if there's a miscalculation or something, but